So it's rather nice that we just derived above threshold, which what it does, let's remind you, is it does a sequence of queries and outputs that they're all below a threshold until it finds the first one, which is above a threshold, and then it says we're above threshold, and then it stops. So it goes until it finds one large query, and then it halts. Well, as a testament to the power of differential privacy, we're going to see now how we can chain this together in order to output not just what the first large query, which is above the threshold, but actually output the first C things which are above the threshold. And we can see that in this SparseVector algorithm, which is algorithm 2 over here. This and the previous figure were both taken from Dwork-Roth, the book. So let's just see how this goes. And it takes in essentially the same parameter as before, except this time it takes in the additional C as well as delta. So C tells how many queries we're going to have, and delta is the delta and epsilon delta dp. For now, let's pretend that delta is equal to 0 and ignore this term here. But let's just say if delta is equal to 0, then we set sigma equal to essentially 2 times C over epsilon. So the claim here, and what I'm going to try to reason about for you, is just to tell you that if you run this algorithm as we show it here, this is exactly equivalent to running above threshold C times in a row. And the results will just follow due to, composition of dp, as well as, combining the accuracy guarantee for multiple runs. Okay, so let's pretend we have that delta equals 0 for now, so that our sigma is equal to 2c over epsilon. And we can see that this follows exactly the same thing, the same pattern as what above threshold did. So I'll highlight sort of the new lines, and we'll look at those as we go. But okay, so those are the new lines. Essentially, everything else is the exact same. So what we do is we start by noising the threshold, and then for each query, what we do is we noise the query as well, and we see whether the noised query is greater than or less than the noised threshold. So let's look at the latter case first. If it's below the threshold, then as before, we just output that bot and continue onwards. However, if it's above the threshold, then we have to do something different. Remember, before, if we saw something above the threshold, all we did was we output top, and then we returned, we halted. However, here what we're going to do is we're going to output top, but then we don't halt yet. We essentially restart the algorithm if we were doing above threshold. And by that, I mean what we do is we increment count, first of all, but then we re-randomize the threshold and then continue. We essentially just keep going. And we keep going and keep going until eventually we reach the fact that count is greater than or equal to C, and then we halt. Essentially, this says, you're running above threshold C times in a row. So once you reach the Cth iteration and you find the Cth discovery, then you halt. So this is exactly just C runs of above threshold in a row. And in particular, you can see that the value of sigma is exactly the same as it was before, how much noise we added at every place. But this time, we've scaled the noise up by a factor of C. Why have we done that? Well, that's exactly just due to basic composition. And similarly, if you're okay with a delta greater than 0, you can get away with scaling it up only by a factor of roughly root C in order to get, and using advanced composition here. So essentially, what I've just argued about here is this is equivalent to running above threshold, C times in a row. And so that gives us the following theorem, that sparse is epsilon delta dp for all epsilon greater than 0 and delta greater than or equal to 0. Cool. So that's the privacy guarantee, which is pretty straightforward to see about. Similarly, the accuracy guarantee is not too hard either. We're not going to go into it and reason about where every term comes from, but at least let me just show you the theorem statement, and we can kind of go over how it differs from before. So you can see, let's focus again on the case where delta is equal to 0, first of all. The theorem says the following. Suppose we're given a sequence of k queries, where only c of them are large. So the number similar to before, the number of I, such that they're above the threshold by, they're above the threshold minus alpha as at most c. So then if we have the delta is equal to 0, like the pure DP case, then it's going to be alpha beta accurate for alpha equal to this value here. So let's compare this to what we had before. What are the differences? Let me highlight them maybe in a different color. The differences are the C here. Yeah, the C is one difference, and the C here is the other difference. So you can see here that, we have these two things that are new. If you set these equal to 1, this gives you exactly the theorem statement we had before. But why do these come up? Well, there's essentially just like looking at the same accuracy guarantee that we had before, but the only differences are this C comes up because we have a union bound. So by that, I mean, before we had that the probability of failure was beta over 2 for this. Well, instead you can set it to be beta over 2C here. And, that's the probability that it fails at any of the C invocations of above threshold. And similarly, what we have here is this factor of C. Where did that come from? Well, that comes from the fact that we, rescaled epsilon by a factor of C. Remember when we were doing advanced or basic composition here, we set epsilon to be, we rescaled epsilon by a factor of C. So that kind of has the correspondence that, here we'll get in an extra factor of C. Sorry, not there. It'll be, I guess, here. Yeah, it should be here in the denominator. And, just kind of putting, if you redo this calculation, you'll see you get the exact same bound that is claimed here. So this is due to union bound, and this is due to composition and scaling on epsilon. And similarly, if you do the same type of reasoning in terms of rescaling, like the union bound here is the exact same in the approx DP case, but here you have to just scale epsilon by a different factor for the approx DP guarantee here. So yeah, this is a very convenient type of algorithm, and it tells us, which of many of a sequence are, greater versus less than some threshold, approximately. And let's just to highlight a few of the salient points, a few more salient points here. Like the one cool thing here is the fact that, again, the dependence on the total number of queries that are asked is logarithmic. So it's only log in k. But what we do pay for is the number of large queries we're looking for, C. So you can see that, we have a polynomial dependence on the large queries, which is kind of unavoidable in some sense. We haven't talked about lower bounds yet, but it's kind of unavoidable in some sense. And a logarithmic dependence on the total number, which might be large. So this is kind of the best we can really hope for. And that's a very powerful type of accuracy guarantee. As one last thing before we should talk about an application of this type of algorithm we'll revisit private multiplicative weights again. Let me just mention that there's also a variant which we refer to as numeric sparse. And numeric sparse lets us also output not only the identities of which are the large queries, but also the values of the large queries. And the idea is the following. Like, recall that right here, we paid linearly in the number of large queries. So if we're already paying linearly in the number of large queries, why don't we just get a little bit more out of it? If we see a large query, why don't we also try to output the value of that large query? And it turns out this isn't too hard to do just by sort of a post-processing type method. So let's see, essentially the only change will be something of the following. I'm not going, this is like kind of informal, but instead of outputting this here, what we do instead of this is we're going to output instead in the numeric sparse version, what we do is output AI is equal to Fi of D plus some new Laplace random noise, Laplace of, and I'll just write this as theta of C over epsilon. I'm just using a theta here because I don't want to worry about the specific constant and what privacy guarantee is. But the idea is, instead of just outputting top, what we're going to do is we're going to, re-noise the value here and output it. And this allows us to output the values of the the large queries, not just the identities. One thing I'll comment about, you're wondering why do you have to re-noise it again? Didn't you already noise it here? You can just use this fi of d plus new of I. Well, the thing is, if you do that, that actually turns out to not be private. So it's very surprising. But like I said, the analysis is tough to get precisely right. So instead, what you do is you find the identity of these large queries and just noise them again using fresh noise, and life is good. The question is, what type of accuracy guarantees do you have? Well, the type of accuracy guarantees is going to be something like the following. Now we're going to have that the output will be a stream of, instead of having, a stream which is like either bot or top to the star, which means like a variable length output. Instead, now we're going to have something which is more like the following. We have, R union bot, and then this whole thing is to the star, I guess. Like, it's an infinite sequence of, or it's a sequence of a variable length sequence of real numbers or bot. And we have the following type of guarantees. The first one is similar to before. If at a specific time that it outputs bot, then that implies that fi on d is less than or equal to t plus alpha. This is just the same as before. If it says small, then it's not too large. And then the other case is if ai is a real number, then we have that essentially it's an accurate estimate of the query. Fi of d minus ai is less than or equal to alpha. So these are the two guarantees that we have. We estimate everything which is large appropriately. I guess we also have the guarantee if ai is in R, it implies first of all that fi is going to be greater than or equal to t minus alpha, but then also it implies that this is an accurate estimate of it. So these are the type of this is the sort of small change in the accuracy guarantees we have from before, and if you do that, then you'll have pretty much the same type of accuracy guarantee as you see here in Theorem 4, up to maybe a constant factor, just because you need to allocate some privacy budget for this last outputting of the Laplace noise to answer the last query. Okay, so that's it for all these different things, and we're going to see now an algorithm or an application of this to revisit the focus of last lecture, which was online. Last lecture we focused on private multiplicative weights. We're going to see how this lets us answer private multiplicative weights or run this algorithm in an online setting. So let's recall what the private multiplicative weights algorithm did in the offline setting. So the idea is we maintained a distribution p hat, which was over the domain elements. So it's a distribution p hat over the domain, which is the set X. And the idea is that the goal was matching the true data set when converted to its histogram representation P on all linear queries in some set Q. So essentially we wanted something like the following. We wanted that, let me write this here. We wanted that F on P hat minus F on, let me say it as follows. So there's a true data set P. And there was a set of queries Q, and we essentially wanted for all F in Q that we wanted a private estimate of what F, for all F in capital Q rather, we wanted that we wanted a private estimate of F on P. And in fact, private multiplicative weights allowed us to do something even stronger than that. It allowed us to get some p hat, which actually, when you subbed it in, it would approximate it on all the queries at once. But we're going to let's recall the algorithm first of all. Oh, one thing I'm going to comment is we're going to change our normalization. So up until this point, we've been focusing on the case where sensitivity. We were looking at sensitivity 1 queries. But now we're going to look at sensitivity 1 over n queries as we were in the previous lecture. In particular, recall that, you know, a query in the previous lecture was something like f is like f on some data set would be equal to, you know, the average value of the summation of f of xi, where f takes in something from the domain and goes to 0, 1. So the idea is, like, we've been talking about sensitivity 1 queries in today's lecture, which you can think of as being sort of just the sum of the values on the things. But now we're going to move back just so that we match what we had in the previous lecture. We're going to have sensitivity 1 over n, just which corresponds to this normalization factor here. Okay, so hopefully this looks familiar. If not, I'd recommend, sorry, maybe I was covering this up with my camera, but hopefully this is visible now. But, you know, this was the setup what we had for the previous lecture, where we averaged a query between 0 and 1 over the data set. And, you know, this corresponds exactly to what we, the change between the sensitivity 1 and 1 over n is just, you know, whether we cancel this 1 over n out or not. Just a normalization. Okay, so what I want to say now is let's recall how the algorithm worked. The algorithm worked as follows. So we started with p hat equal to the uniform distribution on this domain. And we iteratively ran the following 3 steps. So the 3 steps were the following. So we first used the exponential mechanism to choose a large query. So let me recall that this is offline first of all, and we'll see how to go online afterwards. So in the offline setting, this is what we do iteratively for t steps. We're going to first choose a query f in q, which has with large error. And what do I mean by that? I mean a query such that, you know, f when applied to p hat minus f when applied to p is going to be greater than alpha. So the idea is we choose first of all something with a large error as best we can. Well, okay, so sorry, I'm getting a bit ahead of ourselves. Really what we did with the exponential mechanism is try to find something with comparable to the largest possible value of this. So that's the first thing we did. Then the second thing we did was check how large, you know, that f on p hat minus f on p is. If it's like, and then from here, if it was small, if it's small, say less than alpha, then return p hat, because the idea is we've kind of answered all of the queries simultaneously to be accurate. And then if it's large, then you perform multiplicative weights update. And you do this using like the private result using, you know, f on p, but privately. So that was a 3-step approach to doing the exponential, to doing the multiplicative weights algorithm for queries in an offline setting. Use the exponential mechanism, check how much error that had, and if the error was small, then we return. Otherwise, if it's large, then we use the multiplicative weights update. And the thing to note in the last lecture is that we could bound the total number of iterations using sort of these regret bounds as O of log of the domain size divided by alpha squared. So it wouldn't take too many iterations. So what we're going to do is we're going to integrate this with our SparseVector technique. And the question is, the sort of setting now is as follows. We're given k queries, you know, f1 through fk in an online setting, and they're all, and this is sort of equal to the set, they're from some set q. Our goal is slightly relaxed from what we actually gave before. Before, what we gave was that we gave a you know, p hat such that p hat would actually match the answer of the query on all queries in the set of queries at the same time. But we're going to go for, in the online setting, we're going to give something a little bit simpler. We're just going to try to answer the queries as they come. So we want to answer fi at time I accurately. And of course, also privately at the same time. So yeah, the idea is we're just going to try to answer things accurately. We could actually also output a synthetic data set if we wanted, like output a p hat at the end, which would actually be accurate on everything simultaneously. But that's sort of, we're not going to discuss that much. You can think about that if you want, though. And the algorithm is going to be very similar to before. What is the difference going to be? Well, before we just ran the exponential mechanism, but recall that we can't run the exponential mechanism because of the because we're receiving things in an online setting. So let's see what the steps are here. So online. So we're again going to start with p hat being equal to the uniform distribution on the domain, but now we're going to run the sparse vector technique with the sort of on the queries. And the threshold will be, what will be the queries? Like, what are the queries in this case? What do we feed into SparseVector? Well, we're going to use the queries which are the magnitude of, p hat. Let me write it as we've written it in today's lecture, at least. At time I, it'll be the following. It'll be, this will be what the query is, and we'll use the threshold t, which is equal to, say, theta of alpha. I'm not going to worry too much about the specific constants, but essentially what we're going to do is try to mimic what we were doing before. You can see the first two steps, we're really looking to see whether the value of f of p hat minus f of p is going to be greater or less than alpha. And so that's exactly what we do here. We're just going to use SparseVector, checking whether their difference is greater than or less than alpha. So how do we go about this? Well, what we're going to do is the following sort of 3 steps. So at a specific time, if so this is step 1 at each iteration, if sparse returns bot, then what does that mean? If it returns bot, that means that fi on p and the value of fi on p hat are very close to each other. In fact, they're like the distance is less than alpha. So if we wanted to output the value of fi on p accurately, then what we could actually do is just use this value, and that wouldn't pay any additional privacy cost, right? Because the query is public and our data set is already privatized. So just if it returns bot, that means the error between the two is small, and then we can just output f sub I on p hat without paying further budget beyond what we're paying already for SparseVector. So then, on the other hand, if sparse is equal to top, then what we do is we actually now, in this case, what we do, we have a large error with respect to the data set. So what we do is we want to output the correct answer. So what we can do is actually use the numeric sparse technique in the sense that we're just going to output fi on p plus some noise, say some Laplace noise, Laplace of magnitude, say, like, I don't know, plus, let's just say plus Laplace noise. You can work out what the exact value is. I don't want to try to put in the constant so that's right or not. So we're going to output, say, the true query value plus Laplace noise to privatize it. And then we're not done yet, because this will answer the query correctly. But we also have to do an MW update, do a multiplicative weights update. And we do this using this sort of privatization of the value of f sub I on p. And so that's all there is to the algorithm. Essentially, you do the same, you answer the questions one by one as they come. If something is said to be small using the sparse vector technique, then you can just output what you've learned so far using the p hat. On the other hand, if it says that the query is large, then we're going to output the true value plus some Laplace noise and then update. So essentially we don't make the same type of mistake too many times. And if you do these both, then you'll output correct answers as you go. And the question just remains as how you bound, the total privacy cost you pay. What should you set C to be actually? Because how many things can you, how many mistakes can you make and stuff like that? Well, the convenient thing is that it can actually be analyzed very similar to before. In particular, we're going to set C to be equal to this value here. Essentially, before we said that we can't make too many mistakes before we would violate the regret bound. So essentially, the same type of reasoning lets us set C to be equal to log of the size of the domain divided by alpha squared as well. And so, yeah, that's basically all there is to it. Combining the fact that setting C to be the appropriate value, as well as substituting in the appropriate value of rescaling epsilon appropriately and things like that. It's not too hard. I'll let you fill in the details yourself, but it's possible to put these pieces together and then give the online private multiplicative weights update algorithm, which can actually answer a set of linear queries on a database privately, getting the exact same getting the exact same sort of accuracy guarantee as before, except in an online setting. I think this is a good demonstration of how powerful the SparseVector technique really is, because it lets you convert essentially algorithms which may use the exponential mechanism into an online setting if you view it the right way.